All right, good morning, guys. Today we're going to be covering 8.4 arc length of circles. We're going to be introducing radian measures today, so let's go ahead and get started. The first thing that we're going to do is talk about arc length. Arc length is understood to be the distance along a circular arc. It's typically measured in feet or centimeters, but it's going to be in a distance, so it's always going to be a distance unit. So therefore, it's just the distance from point A to point B. And it's going to include all the points that are along this arc here. So the first thing that we need to do in determining the length of arc AB is we're going to go ahead and discover the circumference of the circle. So that's what we need to first find out, the circumference of the circle. To do that, we're going to use our circumference equation. Circumference is equal to 2 pi times the radius. So 2 pi times r. As we can see here, we do have our radius is 9 centimeters. And then the only other measurement that we have is this arc measure, the degree amount of the arc. And those are the only two things that you really need in order to solve the arc length. So let's go ahead and plug in our radius of 9 for r, and then we'll be able to solve for circumference, giving us our circumference is equal to 18 pi. Now that we have our circumference, we're going to go ahead and move on to our second part. We're going to go ahead and set up a fraction to represent the part of the circle's circumference represented by arc AB. So we know that we have a 60-degree angle for arc AB. Now, how many degrees are in a full circle? Well, 360. So if I do 60 divided by 360, that would be a fraction showing the circumference represented by arc AB. It's just that little section there, 60 of 360 degrees of the circle. Once we get our degrees, the next thing that we're going to do is we're going to write an expression using the fraction and the circumference to represent the arc length. So if the circumference is the distance all the way around a circle, and I just want 60 out of 360 degrees of that circle, then I can find my circumference and multiply it by our fraction. So therefore, the arc length will be equal to our circumference times the fraction that we have. And that's our equation. So the final question that we need to know is, what is the arc length? We're going to round our answer to the nearest tenth. So I have my circumference C as 18 pi, and I have my fraction as 60 over 360. So plugging those values in, we get arc length is equal to 18 pi times 60 over 360. Now, of course, 60 divided by 360, that can be reduced down to 1/6. And 1/6 times 18 pi is the same as 18 pi divided by 6, which will just leave us with 3 pi. So therefore, the arc length of arc AB is equal to 3 pi, or about 9.4 centimeters. And that's our final answer in order to find out the arc length of any arc within a circle. So that leads us to a little reflection question. How would you find the length of an arc of the circle that measures m degrees? Well, if it measured m degrees rather than 60 degrees, we just replace our fraction, the numerator in our fraction, with m, or whatever amount of degrees we are given. And that's how we can always find the arc length of a circle. So let's go ahead and break this down into an equation for us. The formula for the arc length of a circle, that equation will be arc length is equal to our circumference times our fraction, meaning our arc degree over 360. Now, circumference will always be 2 pi times r. That's the equation for the circumference of a circle. We take that circumference based upon the radius, and we multiply it by our arc degree measure. So we want that measurement. And then we, of course, divide that arc measure that they give us by 360, the total amount of degrees in a full circle. And that will give us just a fraction of the circle's length, which is exactly what we're looking for with arc length. So let's go ahead and move on towards discovering what radians are and how to use them. So consider a set of concentric circles with center O and radius 1, 2, 3, and so on. Now again, concentric circles just means that the circles have the same center. So this is what it'd look like. I have my circle here, and as we can see, it has radii of 1, 2, 3, so on. And further, this right angle cuts off the arcs to measure 90 degrees. So each of these arcs is a 90-degree measurement. So with this, for each value of the radius, r, meaning 1, 2, 3, or so on, we're going to find the corresponding arc length. So I want to know the arc length of this 90-degree section here. We are going to write our arc length in terms of pi and to the nearest hundredth. Now, it's important to keep in mind that if I answer it in terms of pi, that means that it's going to be in radians, because radians will always be in terms of pi. So here's our table that we're going to be using. As you can see, we have a radius of 1, and then we're going all the way up to 5. I'll go ahead and do example 1 with you, and then give you time to fill out the rest. So to fill out example 1, when the radius is equal to 1, we're just going to plug it into our arc length formula. Arc length is equal to our fraction times our circumference. So I have 2 pi times r for our circumference, which just gives me 2 pi. For our fraction, I have 90 degrees, the angle that we're working with, over 360, which is the same as 1/4. So I have 1/4 times 2 pi. Well, that will just give me pi over 2. So therefore, when my 90-degree angle is cutting off this arc length, and I have a radius of 1, that means that our arc length is equal to pi over 2. Now, if I enter this into the calculator, that will give me it rounded to the nearest hundredth, or 1.57. So go ahead and take a minute, enter in the rest of these into your calculator, and figure out each of these answers. Pause the video if you need to. We'll be starting up again in just a minute. All right, so when you plug these in, you should get, for the rest of the answers, whoops, give you that 5-minute symbol right there, right? For the rest of the answers, when our radius is 2, our arc length is pi. When our radius is 3, our arc length is 3 pi over 2. When our arc length is 4, our radius is 4, our arc length is 2 pi. And when our radius is 5, our arc length is 5 pi over 2. As we can see, all we're doing here is each time that we increase our radius by 1, our arc length increases by r times pi over 2. So each time that we increase by 1, our arc length will increase by the radius times pi over 2. And of course, if I enter in these values into the calculator, I can always get these decimals down below as well. All right, let's go ahead and continue on. Next up, we're going to go ahead and graph each of these points. So go ahead and graph the ordered pairs from your table on the coordinate plane to the right. As I can see, the x-axis is radius. The y-axis is arc length, s. So again, go ahead and label these up as you draw them on the graph. When you graph each of these points, you should get all of these blue points here. What do you notice about the points? Well, as we can see, the way that the points are shaped, the way that they look, these points are linear. So we have a linear function occurring here. And again, it's linear because I can draw a straight line going through all these points, which by definition would make it linear. That leads us to the next question of what type of relationship is the relationship between the arc length and the radius? Well, we can determine this based upon what's occurring when something changes. So we know that this is a linear relationship because by each increase of 1 on the radius length, the arc length will increase by pi over 2. So each time the radius increases, the arc length increases by the same amount each time. It's consistent, which makes it linear. That leads us to our final question. What is the constant proportionality for this relationship? So constant proportionality just means that they're going to be asking for slope. And we know that slope is equal to rise over run. Well, rise deals with our y increase, our y change. Run deals with our x change. Well, our y change is pi over 2, Our x change is 1, so therefore our slope is pi over 2 over 1, which is just equal to pi over 2. So let's go ahead and take a second and reflect for a minute. What happens to the arc length when you double the radius? So we just talked about increasing the radius by 1. Now we're going to talk about doubling the radius. So I'm going to go ahead and make a little table here. Here's my table. And as we can see, the radius is doubling each time. I'm multiplying by 2. What happens to our arc length? Well, it's also being multiplied by 2. It doubles. It doubles each time as well. So arc length is exponential. Radius and arc length go hand in hand. Each time the radius increases, the arc length will increase by a proportional amount. And that's just going to occur every single time, because we can see that the radius is doubling, and we can see that the arc length is also doubling. And so this relationship is very, very close-knit. So the constant proportionality for this relationship is what? Well, we talked about constant proportionality being slope. Well, since this is doubling, it would be our scale factor. What are we multiplying by? Well, we're multiplying by 2, and that would be our constant proportionality here. So this is going to be defined as the radian measure of an angle. And again, radian measures are always written in terms of pi, so keep that in mind as we are working through this. Radian measures are going to be extremely useful when you get to trigonometry and when you're dealing with the unit circle. You're going to use it constantly. So make sure that you guys are comfortable with radian measures as well. They're just going to be written in terms of pi, and you will have to memorize them, but not all at once. You'll memorize them over time as well. But you do need to know the ones for the unit circle. Not necessarily for this course, but down the road you definitely will. So for each increase in radius length of 1 for a 90-degree angle, the arc measure increases by pi over 2. And that's something that we've been seeing with these tables. So think. You know that 360 degrees is the degree measure that corresponds to a full circle. What radian measure corresponds to a full circle? By definition, the circle has radius 1. And again, it has a radius of 1 because we're dealing with the unit circle in this case. So in order to determine this, determine this radian measure, we need to find the arc length of the full circle. Well, to find the arc length of a full circle, that would just be circumference. And we know circumference is equal to 2 pi times r. And if I'm multiplying it as an arc measure, I'll multiply it by the fraction as well. In this case, the fraction would be 360 degrees over 360 degrees. Because again, they're saying that 360 degrees is in the full circle, and that's the arc measure that we're dealing with here. Well, of course, 360 divided by itself is just 1, and our radius is 1 as well, so that's why this 2 pi doesn't have the r next to it, because 1 times 2 pi is just 2 pi. So therefore, we just end up with 2 pi. So within a full circle, there's 2 pi radians, which is equal to 360 degrees, which is 1 full circle. Again, radians and degrees, those are closely knit together as well, because they are just both measures of the amount of openness of an angle. So let's go ahead, and we just talked about a full circle. Next, let's go ahead and measure a corresponding semicircle. So if I have a semicircle, how many degrees are within that open measurement? Well, a semicircle is half a circle, so therefore my radians will be equal to 180 degrees divided by 360 degrees times 2 pi r. And again, radius is still 1. That hasn't changed. Well, 180 divided by 360, that's just 1/2. So I have 1/2 of 2 pi, and 1/2 of 2 pi is just equal to pi. So therefore, in a semicircle, the radian measure would be pi. So therefore, we can say that pi is equal to 180 degrees. Pi radians is equal to 180 degrees, which is the same as a full semicircle. Now, you may be wondering, if these two are so closely related, is there a way that I can move between them? And yes, there is a way to move back and forth between radians and degrees, and it's used very often. We're going to use these proportions, and there is a key to it. There's a key to making this easy. So the first one that we're going to go through is we're given degrees. We want to convert it to radians. So if we're given degrees, what I want to have happen is I want my degrees to cancel. And the only way that I can do that is if I have degrees in a numerator and degrees in a denominator, because then those degree units will cancel each other out through dimensional analysis, which is something that you should learn in your science course, but we use it a lot in here as well. So what we would do is we take the degrees that they give us, and we would multiply it by pi over 180. Now, of course, the degrees that they give us is already over 1. So as we can see, we have a degree in top, a degree in the denominator as well. Those two will cancel each other out, and we'll be left with radians. And of course, radians are in terms of pi, which is exactly what we'll be left with. So let's go ahead and see this in action. And again, the key here is to get these degrees to cancel. So the example that we have is we're given 180 degrees. And we should know this one already because we just did it on the last slide. So we should know what answer we would get. So let's go ahead and see if it works. So I have 180 degrees that they give us. I multiply it by pi over 180 degrees. That will convert it to radians. Now, as I can see, I have degrees on top, degrees down below. Degrees should cancel out, which will leave us with pi over 1. Well, pi over 1 is just pi by the identity property. Anything divided by 1 is itself. That's the identity property. So therefore, 180 degrees is the same as pi radians. Those two those two openness measures are the exact same amount of openness. Next, let's say that we're given radians and we want to convert to degrees. Well, we know that with radians are always in terms of pi. And degrees don't have pi in them. Degrees are just degrees, right? We've never seen pi attached to these degrees here. So what I want to do if I'm converting from radians to degrees is I want the pi's to cancel out. I need to have the pi's cancel. So I need to have a pi in the numerator. That's the one that they give us. And I need to have a pi in my denominator. And that's going to be part of our conversion. So therefore, the radians that they give us times 180 over pi is equal to degrees. And again, we can see that that's just this fraction flipped upside down. And that's all that's occurring here. That's the only difference. So let's say that they give us 3 pi over 4. And you may notice that the pi is on the outside. That pi is still belonging to the numerator, even if it's written like this. This is the exact same thing as 3 pi over 4. So if you ever see the pi written on the outside, it still belongs to the numerator up here. So what we want to do is we want to have the pi's cancel out. Again, that's our key goal here. We want to see those pi's cancel. So therefore, I am going to go ahead and take that 3 pi over 4 and multiply it by 180 degrees over pi. Now, I have a pi on top. I have a pi down below. Those two will cancel each other out. And what I'll be left with is 3 times 180 over 4 times 1. Again, I just multiply straight across here. 3 times 180, 4 times 1. Well, 3 times 180 will give me 540. 540 divided by 4 is 135 degrees. So that would be our final answer. So again, we can convert between degrees and radians just by making sure that either the degree symbol cancels out or the pi symbol must cancel out. Either of those two needs to happen in order to convert between the two. If you don't have them cancel out, you're going to have degrees over pi still, and it's going to cause you issues down the road. So to finish off this video, go ahead, pause the video for a second, try out each of these problems, and then we'll go through each of them and check your work. All right, so the first one we're going to be converting from angles to radians. And the first one that we're given is 60 degrees. So if I'm given 60 degrees, I need the degrees to cancel. So I need to have my degree units in the numerator and the denominator. So I'm going to multiply by pi over 180 degrees. Now, when I multiply by pi over 180 degrees, I multiply straight across. 60 times pi, 60 degrees times pi gives me 60 pi. And then 180 times 1 just leaves me with 180. Now, of course, we already see that the degrees are gone. From here, we must reduce this down. 60 will go into both 60 and 180. So therefore, the 60s will cancel. 60 will go into 180 3 times. So 60 pi over 180 is the same as pi over 3 radians. Next, I do the same thing with 120 degrees. So I'm going to multiply by pi over 180 once again, give me 120 pi over 180. 60 will go into both of these numbers as well. Reducing it down will give me 2 pi over 3. Next, we're going to go ahead and convert from radians to degrees. So for radians, I'm going to go ahead and multiply by just the inverse of this fraction up here. I'm going to multiply by 180 degrees over pi. That way the pi's cancel out. When I do that, I multiply straight across. This will give me 5 times 180 times pi over 6 times pi. The pi's will cancel each other out. If I multiply across from here, 5 times 180 is 900. 900 divided by 6 will give us our final answer of 150 degrees. Last one that we have is 4/3 pi. Again, the pi belongs to the numerator here, so it's actually 4 pi over 3. Again, since we're converting to degrees, we multiply by 180 over pi. That will give us 4 times 180 times pi over 3 times pi. Again, we always multiply straight across with these. There's no equal sign in between, so it's not a proportion. So from here, 4 times 180, that will give me 720. The pi's will cancel out. And then in our denominator, we're left with 3 still. 3 will go into 720 240 times. So therefore, 4 pi over 3 is the same as 240 degrees. All right, guys, thank you so much for watching this video today. If you have any questions, just let me know, but have a great rest.